первые 15 минут, потом пошли заниматься другими делами, потом еще раз включили. Так.
Вообще-то, если без шуток, нас тоже сначала было больше, и пропали люди как раз после той лекции, когда вы ввели конусы и пределы в категории. В общем, ну, совпадение. Нет, ну если честно, я тоже почувствовал, казалось бы, что как будто бы до этого было все то, что, ну, в каком-то виде я слышал, или, сказать, ну, вообще почти слышал, а вот тут началось что-то новое.
В принципе, в следующий раз
тяжелое.
В следующий раз, если будут чуть читать, более, как-нибудь, что ли.
Да не факт, что дело в этом.
Менее категорно, как-нибудь, может быть. Просто через явные конструкции.
Да категорно лучше.
Явно лучше, вот.
Не, ну правда, не то, чтобы я собирался это еще раз слушать. Я и так второй раз.
Да нет, ну, не знаю, я тоже не сказал, что сложность была только в этом, но просто это тоже вот, неожиданно так много всего.
Так, я тем временем проверю, что-то все хорошо, так ничего не видно.
А, может быть, там опять под видом К3?
А, вот там, кстати, тоже ничего не видно. Это, наверное, случайно. Так. Вот где-то здесь надо включить.
Там здесь кнопочки, но вроде не все включены, но все три должны быть включены.
Ну, если выключить так вот, на сторону. Вот я выключил. Это включил.
Учитывая, что сегодня К3 вроде как не было, то, скорее всего, мы под именем К3 сейчас будем.
Ну, это главное, что чуть-чуть видно было.
Что такое К3, простите?
Ну, какой-то алгем К3 поверхности, я в этом не разбираюсь. Просто знаю, что до этого есть курс, который называется К3 Surfaces.
Я понял, забавно. Я просто недавно, типа, ну, меня подвозили на машине, я описал место, так, ну, и, типа, водитель не понял, а с нами был еще один чувак, он сказал, ну, короче, везите его на К8. Я спросил, что
Ну, что ничего не появилось, да?
2 дня подряд.
Ничего не появилось.
И вообще, кстати, камеры просто хотя...
Ну, что вообще что-то выключено. Нет, ну, вроде, то есть, если это работает, там камера, а ну-ка, вот здесь, если так, это с камеры. Да. Общий один. То есть общий вид 1, общий вид 2, общий вид 3. И сохранить. Стоп.
Там только звук или с видео?
Звук есть.
А, видео?
А видео нет. Ну ладно. Сейчас последняя попытка. А там? Ой, нет. Шевелитесь, чтобы вы себе лучше ничего не шевелите. Потому что мог выключил, включил. Это такое. Если сейчас не работает, значит не работает. О! Как кажется, появилось, как ни странно.
Ну вот я проверяю, как...
А, погоди, это вот появился вид доски, как можно нормально выходить.
Ну, вообще да, нам это хватит.
Ну ладно. Господи, проблем приятного.
Я вот как раз только что понял, что это должно так работать, и протестировал.
Ну, просто
Оно тут появилось?
тут пока нет, то залишь все это.
Ну, не большой.
Секунд 20.
Вот эти маленькие рейтинги отличаются. Общий вид 1, общий вид 2. Вот этот общий вид 1, может быть, как-то выключить. А может быть.
Не, ну там они оба видны.
Так, ну а тут все не видно. Сейчас.
Не, видно.
Видно?
Я вот открыл, там и вон та полоска, и вот эта закорючка, и то, и другое есть.
Ну ладно, тогда мне чуть не видно, но если вам видно, значит вам что-то все видно. Вы начинать, наверное. В общем, я думал, мы уже все начали приложение. Okay, so at the previous lecture we proved that in many standard categories of locally complex spaces, the projective tensor product preserves co-kernels. And as a corollary, we deduced the following result. If we have two open continuous linear maps, phi1 and phi2, then their uncompleted projective tensor product is also open. And for the completed projective tensor product, we observe the following fact. If phi1 and phi2 are strict, phi1 and phi2 are strict with dense ranges, then so is their complete projective tensor product. And finally, we have a metric result. If the spaces are semi-ordered and the maps phi1 and phi2 are coisometries between semi-ordered spaces, then so are the tensor product, the uncompleted projective tensor product and the completed projective tensor product. So, in fact, these results could be proved directly without any reference to co-kernels, but the direct proof it does reveal the category theoretic meaning of this result. So everything actually follows from the fact that our functors preserve co-kernels, which is actually stronger than what is written down here. Roughly speaking, these results mean that the projective tensor product preserves quotients. Because, so what is an open map? An open map is essentially the quotient map, that is the canonical map from the space to the quotient modulo vector subspace. And what is the strict map with the dense range? This is the canonical map, again, up to an isomorphism. This is the canonical map from the space to the completion of the quotient. So in the general case, the quotient space modulo closed subspace is not necessarily complete. But if we embed the quotient into the completion, then what we get, the resulting map with the exactly strict map with dense range. So the second statement roughly means that our functor preserves quotients in the complete category, the category of complete locally complex spaces. And this is a metric analog for semi-ordered spaces and for bounded spaces. In the case where our spaces are Fresher spaces, we can say more. Actually, everything follows from the next classical result, which is the open mapping theorem, due to Banach. The open mapping theorem. It states that you have two Fresher spaces x and y, Fresher spaces, and phi is a surjective continuous linear map x onto y, then phi is open. Okay, so I'm assuming you know this result in the context of balance spaces. So now an exercise for you is to take your favorite proof of this result for balance spaces, to make suitable little modifications, and to see that actually the result extends to arbitrary Fisher spaces. So the proof is almost the same as in the case of balance spaces. If you now combine this result with the fact that the projective tensor product preserves quotients, we get the following corollary. You have Fisher spaces x1, x2, and y1, y2. Fisher spaces. And two continuous surjective linear maps, phi1 and phi2. Then their completed projective tensor product is also surjective. Well, indeed, they are surjective, so the open mapping theorem implies that they are open. And if we now apply this result in the second line, we see that this map is strict with dense range. But since it acts between Fisher spaces, and it's clear that, well, it's clear that the projective tensor product of two Fisher spaces is a Fisher space. Since it acts between Fisher spaces, it is actually open, because the quotient of a Fisher space modulo a closed vector subspace is also a Fisher space. So we don't have to take the completion. In other words, we have already noticed this at the previous lecture, that a strict map with a dense range between Fisher spaces is actually open. That's objective. Okay, so in summary, we see that the projective tensor product preserves quotients in a suitable sense. Now the actual question is, does it preserve subspaces? And in general, the answer is no. A warning: if we have two topologically injective maps, phi1 and phi2, in general, this doesn't imply that their projective tensor product, or the completed projective tensor product, is topologically injective. The counterexamples are not very simple, so probably I'll include one of them into the next exercise sheet. But anyway, the projective tensor product doesn't respect subspaces. So our next goal will be to observe that if we replace the projective tensor product by the injective tensor product, then the situation is just the opposite. The injective tensor product preserves subspaces. And more exactly, we have the following result. Theorem. You have two continuous linear maps between locally conic spaces xi and yi. So if phi1 and phi2 are topologically injective, and so are their uncompleted injective tensor product and the completed injective tensor product. And also, we also have a metric analog of this result. Namely, if our spaces are semi-normed spaces, if xi and yi are semi-normed spaces, and the phi1 and phi2 are isometries, then so are their injective tensor products, the uncompleted and the completed injective tensor products. To prove this theorem, we need a simple lemma, which is actually a simple exercise in the classical functional analysis. Suppose that we have cylinder spaces x and y, and a continuous linear map phi from x to y. Well, I claim that if phi is an isometry, then the dual map phi prime is a co-isometry. And second, if phi is a co-isometry, then the dual map is an isometry. Okay, so this is a simple exercise in functional analysis. I assume you already know this in the context of norm spaces, and for semi-norm spaces, the proof is essentially the same. Now it's rather easy to prove our theorem. In fact, it's enough to look at part 2. It's more convenient to start with the second part. So we have semi-norm spaces xy and xi and yi, and triisometries, y1 and phi2. So essentially we draw the same diagram, which we have already considered when we proved the functoriality of the injective tensor product. So let's recall this diagram. So this is the map we are interested in, the uncompleted injective tensor product. We want to show that this is an isometry. Now recall that this space, the injective tensor product of x1 and x2, is canonically mapped to the dual of the projective tensor product of the duals. And this canonical map is an isometry. And similarly for y1 and y2. And here we have the dual of phi1 prime tensor phi2 prime. And the diagonal commutes. And this is also an isometry. So this picture essentially completes the proof of part 2, because since phi1 and phi2 are isometries, these dual maps are co-isometries, but we know that the projective tensor product of two co-isometries is a co-isometry, and now we apply our lemma and conclude that this arrow is an isometry. So this is an isometry, this is an isometry, this is an isometry. As a result, we see that the bottom arrow is also an isometry. And that's it. This completes the proof in the case of the uncompleted injective tensor product by taking the completions, so we get the respective result for the completed injective tensor product. And part 1 easily follows from part 2. This is a simple exercise for you. Okay. Of course, a more general question is, how about kernels? So, since the injective tensor product preserves subspaces, it's natural to expect that it preserves kernels. This is indeed true if we look at the uncompleted injective tensor product. A simple exercise, which is actually a combination of this theorem with some basic pure algebraic properties of the tensor product. If say psi is the kernel of map phi in the category of locally convex spaces, then for every locally convex space y, the uncompleted injective tensor product of phi and the identity map of y is psi and identity map of y is the kernel of phi tensor y. Unfortunately, for the completed injective tensor product, the result fails. Again, the counterexamples are not obvious, but they exist. The completed injective tensor product in general doesn't preserve kernels. Again, this is related to the famous approximation property. If we work only with spaces with the approximation property, then one can show, this is not easy, but this is a rather interesting theorem, that for spaces with approximation property, this functor preserves kernels. But for arbitrary spaces, this is not true. Okay, let's now look at another nice property of tensor products. Of course, we know that if we take the algebraic tensor product of two vector spaces, then every element in the algebraic tensor product can be written as a finite sum of elementary tensors. If you now take the complete projective or the complete injective tensor product, since it is the completion of the algebraic tensor product, it follows that every element in the completed tensor product can be approximated by finite sums of elementary tensors. It turns out that for metrizable spaces and for the projective tensor product, we can say more. We have the following theorem. Suppose that x and y are metrizable locally convex spaces. Then I claim that every element u in the completed projective tensor product has the following form. It is the sum of a series of 1 to infinity lambda I xi yi where lambda I are numbers such that the series converges. And xi and yi converge to 0. Xi converges to 0 and yi converges to 0. So this is stronger than the trivial statement that you can be approximated by finite sums of elementary tensors. Here we claim that U is a sum of suitable series, which is quite convenient, as we'll see later. So to prove this result, we choose a defined sequence of semi-norms on x and y. Without loss of generality, we may assume that they are increasing. I define sequence of semi-norms x. And we choose that we will use the same symbols to denote defining family of semi-norms on y. This doesn't lead to confusion because, just like in the case of normal spaces, we always denote the norm by the same symbol and for all spaces and this circuit. Okay, so we have chosen such a family for x and for y, and let's also denote the respective projective tensor semi-norm on the tensor product by the same symbol like this. Okay, we now use the fact that U can be represented by, can be approximated by elements from the algebraic tensor product. And by induction, by using induction, we can find elements u1, u2, and so on in the algebraic tensor product of x and y, such that u minus their sum of ui from 1 to n is so small that the seminorm number n plus 1 is less than 1 over n plus 1 squared 2 to the power n plus 1. This is always possible because, the algebraic tensor product is dense in the completed projective tensor product. Let's now estimate the nth seminorm of un simply by the triangle inequality. The nth seminorm of un is, this is true for n plus 1, so this is also true for n, because they are increasing. And this can be estimated as this number, 1 over n plus 1 squared, 2 to the power n plus 1, plus a similar expression, but for with n plus 1 replaced by n. So this will be 1 over n squared, 2 to the power n. And this can be estimated as 1 over n squared. And here we take 2 to the power n minus 1. I hope this is true. Okay. Is that correct? Well, this is less than 2 to the power n. This is less than n squared, and 1 over 2 to the power n plus 1 over 2 to the power n is 1 over 2 to the power n minus 1. Okay? Okay, so this is an estimate for un. Now recall the definition of the projective tensor seminorm, now on the algebraic tensor product. Here it's in the algebraic tensor product. And this implies that un can be represented as the following sum. Lambda I, xi, yi. And we choose the numbering in such a way that I ranges from kn plus 1 to kn plus 1. Such that the following seminorm, more exactly the following sum, from over the same I is less than this number, 1 over n squared 2 to the power n minus 1. Just by the definition of the projective tensor seminorm. Now, if we now rescale our vectors in a suitable way, we see that we may assume that the nth seminorm of xi is less than 1 over n, the nth seminorm of yi is less than 1 over n, and the sum of the numbers lambda I, again from kn plus 1 to k sub n plus 1, is less than 1 over 2 to the power n minus 1. We simply multiply these three numbers, lambda I, xi, and yi, by suitable real numbers in such a way that these estimates hold. Okay, now, so we have done this for all n. And if you now combine this with this estimate, that's B star, you see that now star implies that u is the following sum, now from 1 to infinity. So each un has this form. So if we now take the sum over n, we get lambda I, xi, yi. And the sum of all lambda I
from 1 to infinity is less than the sum of this over n. So this is finite. This is finite. And xi converges to 0 because of, oh, this is the nth semi-norm, sorry. Xi converges to 0 because of this estimate, and yi converges to 0 because of this estimate. So this is what we're looking for, what we need. Okay. So as a corollary, we see that if x and y are norm spaces, x and y are norm spaces, then every element mu in their projective tensor product, in their completed projective tensor product, has the following form. The sum of a series xi, yi, from 1 to infinity, where the series is absolutely convergent.
Извините, а как мы в доказательстве проверили, что когда мы ОН подменяем на такую сумму, у нас промежуточные суммы не отклонятся далеко?
Так у нас же каждый слагаемый оценивается.
Не сильно так.
У нас просто каждый слагаемый по отдельности оценивается вот так, как тут написано.
Да, это очень сильно. Да?
Поэтому да, потом просто просто группируем первую группу слагаемых, вторую, третью и так далее. В итоге все выстраивается вот в такой вот ряд.
А можно при этом сказать, что эта сумма, она еще и равна норме, которая меньше бесконечности?
В точности равна?
Да.
Вообще говоря, нет.
Такое представление не
вот где? Вот здесь?
Да. Хотелось бы.
Вот здесь можно. Для флеше там вообще как-то особо не очень понятно, в каком смысле говорить про равенство норм, то есть счет лямбда и t. Да, здесь можно, но я про это явно не сказал, но в общем это упражнение. So the projective, in fact, we can choose xi and yi in such a way that the projective tensor norm of u is almost, well, up to an arbitrary epsilon, or almost the sum of the series.
Что ты равенство?
Yeah, no, not exactly. Yeah. Just like in the uncompleted projective tensor product, we can always write U as a finite sum of finitely many tensors, but I don't claim that we can always find that the infimum, which appears in the definition of the projective tensor semi-norm, I don't claim that this infimum is always attained, even for the uncompleted projective tensor product. Okay. Our next goal will be to discuss a very nice and useful and important class of spaces, the so-called nuclear spaces. Nuclear spaces are defined in terms of nuclear operators. So let's first discuss nuclear operators. For technical reasons, it is more convenient to define nuclear operators first in the case of bound spaces, and then to extend the definition to the case of arbitrary locally complex spaces. So suppose that x and y are bound spaces. And let's look at the following picture. So we take the product of y prime and x and consider the bilinear map from this space to the space of continuous linear operators from x to y, which takes every pair f. That's wrong. Y and x prime. Y and the dual of x. So our map, our bilinear map, takes each pair y and f, where y, little y goes to y, and f is a linear function of x. So this map takes yf to the following rank 1 map. So the notation is self-explanatory. It takes x to f of x multiplied by y. One map. By the way, let's observe that the norm of this rank 1 map is easily seen to be equal to the product of the norm of x and the norm of y. So this bilinear map is bounded, or equivalently continuous. And of course, we know that L of xy is a Banach space. So we can, by using the universal property of the projective tensor product, we can linearize this map and consider the linear map, which will be denoted by gamma xy, or simply gamma, from the complete projective tensor product of x and y to the space of linear operators. We now give the following definition. We say that a continuous linear map phi from x to y is nuclear, in Russian, ядерный, if it belongs to the range of gamma. And the space of all nuclear operators, that is the range of gamma, will be denoted by script n of x and y. The space of nuclear operators. A little exercise is that if we look at the image of the algebraic tensor product, which is of course smaller than the completed projective tensor product, then what we get is exactly the space of continuous linear maps of finite rank. The space of continuous linear maps of finite rank. So now it follows from our definition that every continuous linear map of finite rank is nuclear. Also, a simple algebraic exercise is that if we restrict gamma to the algebraic tensor product of y and x prime, then this map is injective. But again, it turns out that in the general case, gamma itself is not necessarily surjective. And again, as usual, this is related to the approximation property. If we consider only spaces with the approximation property, then gamma will be injective. Will be injective. But in the general case, it is not injective. It can have an untrivial kernel. So the space of nuclear operators can be algebraically identified with the complete projective tensor product of y and x prime modulo the kernel of gamma, which is often trivial, but in the general case it is non-trivial. And this algebraic equality can be made into an isometric isomorphism if we simply equip the space of nuclear operators with the respective quotient norm. The respective norm is called the nuclear norm. The nuclear norm on the space of nuclear operators is the quotient norm of the projective tensor norm on the tensor product. And it will be denoted like this. we equip the space of nuclear operators with the nuclear norm, then we get an isometric isomorphism. Okay. The following proposition gives several equivalent characterizations of nuclear operators. So as before, we assume that x and y are bounded spaces, and phi is a continuous linear operator from x to y. Then the following conditions are equivalent. Condition 1, phi is nuclear. Condition 2, phi is the sum of an absolutely convergent series of rank 1 operators. N is a rank 1 operator, and the series is absolutely convergent. Condition 3, phi can be written in the following form: the sum from n from 1 to infinity, lambda n, fn, rank 1 operator corresponding to fn and yn, where the sum of the absolute values of lambda n is convergent, and fn and yn are bounded sequences. Fn is a bounded sequence in x prime, yn is a bounded sequence in y. And property 4 is the same as property 3, but now we assume that fn converges to 0 and yn converges to 0. So to prove this result, we will use our earlier result about the completed projective tensor product. So we already know that every element of the completed projective tensor product can be represented as the sum of a series. Let's look at this result once again. Oh, sorry, this is not here. It's, So we use this result, and we see that if phi is nuclear, so it came from here, and every element in here is the sum of a suitable series. So we now see that 1 implies 4. This follows from the series decomposition elements of the completed projective tensor. Okay, it's clear that 4 implies 3, of course, and also clearly 3 implies 2. This is a rank 1 operator. So this is clear. And 2 implies 1 is also rather easy, because since phi n is a rank 1 operator, we can always write phi n in the following form, where fn is in x prime, yn is in y, and the norm of phi n is the product of the norms of fn and yn. So we now see that phi comes from the following element in the projective tensor product, namely from the element u, given by the following formula. And the series is absolutely convergent in the tensor product. Okay, so this completes the proof. We also have the following useful property of nuclear operators. Before we prove it, let's first of all observe that this proposition, little observation. This proposition implies that every nuclear operator between Banach spaces is compact. Well, indeed, every nuclear operator has this form, but of course, every phi n is compact, and the sum of finitely many compact operators is compact, and so phi is the limit of a sequence of compact, actually finite rank operators, so it's compact. The converse is not true, and we will see this in a minute by looking at a concrete example. Another useful property of compact operators, of nuclear operators, which is in fact similar to respective property of compact operators, and it looks as follows: if you have two continuous linear maps between Banach spaces x, y, and z, so this is phi and this is psi. If phi or psi, either of them, is nuclear, then so is their composition. Phi or psi is nuclear, then phi is also nuclear.
I'm sorry, nuclear operators is not exactly the closure of finite rank operators.
No.
No?
If we look at, for example, Hilbert spaces, then the closure of finite rank operators is the same as the set of compact operators, and the set of nuclear operators is much smaller. It is somewhere in between finite rank operators and compact operators. And somewhere in between finite rank operators and approximable operators. Approximable means which can be approximated by finite rank operators.
Это, кстати, мелким шрифтом в книжке Хелемского хорошо написано. Которая лекция по национальному анализу.
Well, why is it so? Well, actually, this is a simple exercise. Again, just look at, for example, at part 2. If phi is the sum of an absolutely convergent series of rank 1 operators, then the same is true for psi phi. And similarly, if the same argument shows that if psi is nuclear, then psi phi is also nuclear.
X и Z здесь банаховые.
Yeah, X, Y, and Z are Banach spaces so far, and we'll see soon how this could be extended to locally convex space. But at this point, they are Banach spaces. Okay, let's now look at some concrete examples. Example exercise 1. Let's look at diagonal operators. So suppose that P is a real number between 1 and plus infinity, and let X be a little P space or the little C0 space of sequences vanishing at infinity. We take a bounded sequence alpha n and consider the diagonal operator m alpha from x to x, which acts by the well-known formula. It simply multiplies every sequence pointwise by alpha. The diagonal operator. It's a standard fact that M alpha is bounded for the continuous, and the norm of this operator is the L infinity norm of alpha. It's also a standard fact of functional analysis that M alpha is compact, if and only if alpha n converges to 0.
So initial question is, when is it nuclear? And here's the answer. So an exercise is to prove that M alpha is nuclear, even only if the series of alpha M is absolutely convergent. Which is of course stronger than the previous property. So this example already shows that a compact operator is not necessarily nuclear. A hint, and at the same time a some exercise, is as follows. Let's choose a Q in such a way that 1 over P plus 1 over Q is 1. And let's consider the following subspace D in the tensor product. So let me write it down here. So G will be the closure of the linear span of all elements of the following form: En tensor En. And we consider the space as a subspace in the projective tensor product of LP and LQ. As usual, by En I denote the sequence with 1 in the nth slot and 0 elsewhere. So the sub-exercise is to prove that G is isometrically isomorphic to little L1. So once you prove this isomorphism, so it's in some sense the diagonal in LP tensor LQ is isomorphic to L1. So once you prove this isomorphism, you'll easily deduce that this nuclearity criterion for the diagonal operation. Okay, another example. Example exercise 2. Let's denote by I the closed the closed interval on the real line, an arbitrary closed interval on the real line. Let K be a continuous function on the square, I squared. And let's consider the integral operator, phi, on the space of continuous functions, C of I. Given by the following well-known formula. The exercise is to prove that it is nuclear. And find explicitly its nuclear norm. Okay, so these are the basic examples of nuclear operators, and some more examples will be in the exercise sheet. Okay, let's now extend our definition of a nuclear operator to the setting of local atomic spaces. So from now on, we suppose that X and Y are local atomic spaces. The shortest definition looks as follows. We say that a continuous linear operator at phi from X to Y is a nuclear if there exists a commutative diagram of the following form: X, Y, this is phi, E, F, psi, and 2 arrows here and here, where E and F are Bach spaces. E and F are Bach spaces, and psi is a nuclear operator between E and F. And vertical arrows are just continuous linear maps. So roughly this means that we say that linear operator between locally convex spaces is nuclear if it factorizes through a nuclear operator between bound spaces. First of all, let's observe that this definition is consistent with our earlier definition of nuclearity for bound spaces. This is consistent with our earlier definition if x and y are also bound spaces. Well, indeed, they are bound spaces, and if phi can be factorized in this way, then of course phi is also nuclear because we have already observed that the composition of a nuclear operator and the continuous linear operator between bound spaces is also nuclear. And the other way around, of course, if phi is nuclear in the sense of our earlier definition, then we might just take E equals x, phi equals y, and the vertical arrows are just the identity maps. And as in the case of bound spaces, we denote by the space of all nuclear operators from x to y by n of x, y. The natural question is, maybe there is no need to consider bound spaces first. Could we also define nuclear operators between locally convex spaces in exactly the same way as in the case of bound spaces? That is, by considering completed projective tensor products. The problem here is that if x and y are locally convex spaces, then the space L of xy doesn't have any canonical topology, making it into a complete locally convex space. So as a result, in general, we cannot linearize this bilinear map through the completed projective tensor product. Now, this is not the only problem with this definition. Even if this space has a topology making it into a complete space, and sometimes this is indeed the case, for example, when x and y are Fouché spaces. Even in this case, the same definition extended to trivially extended to locally convex spaces gives us not the class of maps we are looking for. In particular, sometimes even the identity map belongs to the image of gamma, which is not convenient, of course. For example, because the identity map is not compact. This is the reason why we have to define nuclear maps first in the case of bound spaces, and then we extend it to locally convex spaces in this way. Well, the definition is short and natural, but what is not clear here is that how could we verify this definition in concrete cases? In particular, where can we find E and F? So our next goal will be to show that we actually can choose E and F in the almost canonical way. Let's make a short digression. So to understand where to find E and F, let's make a short digression. Let's discuss two general constructions of bound spaces. Two constructions of bound spaces. So suppose that X is a locally convex space. Actually, the first construction is already familiar to us, and we consider this construction when we discussed the completion of a locally convex space. So for every continuous seminorm P on X, we denote by XP the norm space constructed as follows. We consider the quotient of X modulo the kernel of P, and we equip it with the quotient norm of P. This is a norm space.
And we denote by x p tilde the completion.
Взять один сум, найти всех.
No, it's enough to consider only this one. Of course, we could take the L1 sum, but this is not necessary for our discussion of nuclear operators. This is the completion of xp. And we denote by pi p the quotient map from x to xp tilde, which is, we can say that this is quotient map only algebraically, but not topologically, because the topology of on xp tilde is not the same as the quotient topology in the general case. It is weaker than the quotient topology, because we remember only one seminorm here. But nevertheless, it is continuous. This is a continuous linear map. Let's now look at another construction of Banach space. Construction 2. Suppose that B is an absolutely convex bounded set in X. And let XB denote the linear span of B. Or equivalently, since it is absolutely convex, this is equal to the union over all nature of N of ND. So this is vector subspace of X, and we consider the space as a semi-normed space equipped with the Minkowski function of B. This is a semi-normed space. And let JB denote the inclusion map of XB into X. It's a simple exercise to show that JB is always continuous. I'd like to stress once again that the topology on XB is not the topology induced from X. This is a topology generated by the Minkowski function of B, and in general, this topology will be stronger than the topology induced from X. But nevertheless, JB is continuous. JB is continuous, and if we know that if X is Hausdorff, then XB is actually a Normed space. Essentially because in a Hausdorff locally convex space, a bounded set can never contain a line, can never contain the proper non-trivial vector subspace. So it is a Normed space. In many concrete cases, this is a Banach space, and there is a special terminology for this. We say that B is a Banach disk. Banach disk. If XB is a Banach space. And here's a typical example. And an exercise at the same time. If X is Hausdorff, if X is Hausdorff, and B is absolutely convex, bounded and complete, then it is a Banach disk. P is Banach disk. In particular, if X itself is complete and B is absolutely convex, bounded and closed, then it is complete, and so it is a Banach disk. A simple property of Banach disks is that the continuous image of a Banach disk is a Banach disk. So if phi is a continuous linear map from X to Y, and B is a Banach disk in X, then its image phi of B is a Banach disk in Y. Well, actually, the explanation is very easy. It's enough to observe that the space generated by phi of B is actually a quotient of xb. And a quotient of a Banach space is also a Banach space. Here's another typical and useful example of a Banach disk, which also relates our two types of Banach spaces associated to a locally convex space. So the first type of Banach spaces, the first type of a Banach space associated to a locally convex space comes from a continuous seminorm on X. And the second type comes from a Banach disk. And so this example shows the relation between these two constructions. So suppose that X is a locally convex space, and P is a continuous seminorm from X. Let's denote by B P the space of those continuous linear functionals on X such that they are dominated by B in the following sense. I claim that this is an exercise that BP is a Banach disk in the dual space, and the respective Banach space X prime generated by this Banach disk is isometrically isomorphic to the dual of XP, or equivalently isometrically isomorphic to the dual of XP tilde. Well, I'm slightly cheating here because in general X prime is just a vector space, so we don't introduce any topology on X prime. But the definition of a Banach disk, let's observe that the definition of a Banach disk makes sense for any vector space X. So we take an absolutely convex subset B of X. We may define XB in exactly the same way. We equip it with the Minkowski functional, so sometimes it's a Banach space. So the definition makes sense for any absolutely convex subset of any vector space. So here we simply consider BP as a subset of X prime, and we don't need a topology on X prime to define it. Okay, so let's now answer the initial question about the Banach spaces E and F, which appear in the definition of a nuclear operator. So we have the following characterization of nuclearity for operators between locally convex spaces. Proposition. Suppose that X and Y are locally convex spaces, and phi is a continuous linear operator from X to Y. Then the following conditions are equivalent. Condition, I forgot to give another important definition, which is essential for this proposition. So before I state this proposition, let's recall what an equicontinuous set is. Probably you know this, but let's recall this. Suppose that we have two locally convex spaces, or just arbitrary topological vector spaces, X and Y. Topological vector spaces. And suppose that, let's say, S is a set consisting of continuous linear maps from X to Y. We say that S is equicontinuous. S is equicontinuous. In Russian, равностепенно непрерывно. If for every neighborhood of 0, neighborhood of 0, say V, in Y, there exists a neighborhood of 0, U in X, such that every operator from S takes U to V. Phi of U is contained in V. Of course, we can always find an individual U for every phi, because phi is continuous. So here the point is that we can find U which works for we can find U which works for all phi in our family. For example exercise: if X and Y are Norm spaces, X and Y are Norm spaces, then S is equicontinuous, even only it is bounded for the operator norm. S is bounded with respect to the operator norm in the space of continuous linear operators. Another simple special case, example exercise: if Y is the base field of real of complex numbers, then a subset S of X prime is equicontinuous, even if all functions from S are dominated by the same continuous seminorm. There is a continuous seminorm P of X such that for every F in S, the following inequality holds. Again, if S consists of a single functional, then we know that this condition is equivalent to the continuity of F. Again, now the point is that we can find the same P which works for all functionals in S. So this is equivalent to the equicontinuity of our Okay, now we are ready to give the following criterion of inequality for a linear operator between locally convex spaces. So suppose that X and Y are locally convex spaces, and phi is a continuous linear map from X to Y. Then the following conditions are equivalent. Condition 1, phi is nuclear. Condition 2, phi can be written in the following form: sum from n to infinity, lambda n, fn, yn. So again, just like in the case of bounded spaces, we have a similar series of rank 1 operators, where the series of lambda n is absolutely convergent, again, just like in the case of bounded spaces. But we have a slightly different condition on fn and yn. So fn is an equicontinuous sequence in X prime, equicontinuous sequence in X prime, and Yn is contained in a suitable Banach disk. In Y. Yn is contained in B for some Banach disk. B in Y. condition 3. Condition 3. There exists a continuous seminorm P on X. There exists a Banach disk B and Y. And there exists a nuclear operator between the Banach spaces X, P tilde and Y, B, such that the following diagram commutes. This is X, this is Y, this is our operator phi. Here we have the canonical map pi p from xp to the Banach space xp tilde. Here we have the inclusion of the Banach space yb into Y, which were denoted by JB. And here we have the map psi, such that this diagram commutes. In other words, if you look at our original definition of a nuclear operator, we see that we can choose E and F more or less canonically, so they are associated to X and Y in this way. Okay, let's fill this result. Let's show that 1 implies 2. 1 implies 2. So phi is nuclear, so we just rewrite our original definition of nuclearity. It is phi. Here we have Banach spaces E and F. So E and F are Banach spaces. Psi is a nuclear operator between E and F. And here we have two continuous linear operators, alpha and beta. Okay, so psi is nuclear, so psi can be written in the following form. The sum over n, lambda n, gn, zn, where lambda n is absolutely summable. And let's choose gn and zn in such a way that their norms, they are in the unit balls. The norm of gn is less or equal to 1, and the norm of zn is less or equal to 1. So gn are, they are continuous linear functionals on E, and zn are elements in F. So now we compose psi with alpha and beta, we get phi, and we see that phi can be written as the following sum, where yn is just the image of zn, where yn is beta of zn. So zn sits in the unit ball of f. So this sits in the image of the unit ball of f. And we have always observed that the image of a Banach disk is a Banach disk. Clearly, the closed unit ball of a Banach space is a Banach disk. So beta of f is a Banach disk. And what is Fn? Well, Fn is just Gn composed with alpha. But Gn sits in the unit ball of the dual space of E, and this easily implies that the sequence Fn is equicontinuous. Fn is equicontinuous in X prime. And that's it. So we get the composition of this form. Okay, so we now see that 1 implies 2. Let's now prove that 2 implies 3. So we write phi in the following form. As 2. So we already have B. So B is the same B as in condition 2. This is a bound disk containing all vectors yn. What is P? Well, Fn is an equicontinuous sequence. Fn is equicontinuous. This implies that there exists a continuous semicolon P on X such that all the functionals Fn are dominated by P in the following sense. And since we have this inequality, we see that each subfunctional Fn factorizes through xp tilde. Fn has the form Gn composed with P pi p tilde, where Gn is a continuous neurofunctional on x p tilde, such that the norm of Gn is less than or equal to 1. Well, why is it so? First of all, we factorize Fn through the quotient of x modulo P modulo the kernel of x modulo the kernel of P. This is possible because if this is 0, then this is also 0. So Fn is factorized through the uncompleted xp. And the same inequality holds on the quotient on xp, so we simply extend the respective function on xp by continuity and we get Gn. Okay, so we see that we have a sequence of functionals Gn on xp, and now it's very easy to construct psi. So psi is simply the sum of the following series: lambda m psi Gn, lambda m Gn multiplied by Yn. Gn is bounded, Yn is bounded in Yb, because Yn is contained in B. So this is a nuclear operator from x p tilde to Yb. And we get condition 3. And implication 3 implies 1 is trivial. This is clear just by the definition of a nuclear operator. Okay, so this completes the proof. It's time to finish, sorry. Okay, that's all for today. At the next lecture, we start with some very simple properties of nuclear operators. In particular, we will see that every nuclear operator factors through a Hilbert space, which is also quite useful. And then we introduce and study nuclear spaces, which are defined in terms of nuclear operators. We will see in particular that there are many natural examples of nuclear spaces, including many Kyoto sequence spaces, spaces of smooth and low conference, and also there are some other natural examples. On the other hand, we will see that a normed space is nuclear if and only if it is finite dimensional. So in some sense, we have two classical and good classes of locally convex spaces. The class of bound spaces, which you know from your course of functional analysis, and the class of nuclear spaces. Both classes are very natural and nice, but they are almost disjoint in the sense that the intersection consists exactly of finite dimensional spaces. But there are many concrete situations in which nuclear spaces are much better behaved than bound spaces.